Hi guys, it's Mr. T here, and we're at my virtual beach here, and I'm gonna try to help you out with some matrices, and we're gonna and SAVVAS topic 10, section 1, operations with matrices, and our goal for today will be I can interpret the parts of a matrix and use matrices for addition, subtraction, and scalar multiplication. And some of the vocabulary here listed would be equal matrices and scalar multiplication, and zero matrix. And those should be pretty self-evident in themselves. And then the essential question being, how can you interpret matrices and operate with matrices? The good news, this is pretty intuitive stuff, but I just want to go over several different pieces of it. And we've already done a little bit with matrices beforehand. So I'll do a little bit of review of that and then move forward from there. So I'm going to get rid of my face today because a lot of these slides, I don't really have anywhere to put my face. So nice chance. Get scared? Bye. All right, here we go. All right. So before we go any further here, let's see this. We open up in this lesson with a model and discuss kind of question. They said the screen shows the number of small, medium, large, and extra large limited edition silkscreen shirts on sale at an online boutique. Okay, now what is a boutique? Well, that's a shop that sells clothes, and more often not, they're cute clothes or something like that. But no, this is a shop that sells clothes, a little shop. Okay. Um, Help interpret that for some of us who didn't know what that word meant. But here we go. We got a little shop sell some clothes, and it's a specialty shop because they sell these kind of special T-shirts. And we're going to construct a table to summarize the inventory that is on sale. Okay, so this table is going to be a matrix. Okay, and so what I've gotten here, and I've decided to put the red ones on the first row. If you follow along the bottom here, and the reason for that being, okay, because in part B, they list the red first. So I went ahead and started with red here. It's no rule, just got to know which one's which is all. We just got to have an agreement. And then blue for the second, and we got those from here, okay? So we know anything in the first column is the small t-shirts, whether it's red or blue. Second would be medium, third be large, and extra large for the fourth column, right? We said column, rows by columns, so in a matrix, we that's how we identify. It's got 2 rows and 4 columns. Okay, and then let's go to the next piece here. At the end of the day, the boutique has sold this many of each T-shirt from the sale items. So they've sold 4 red smalls. So okay, I got that down here, and 6 red mediums, 3 red larges, and 5 extra larges. And this is at the end of the day. And you notice what I don't have. I don't have any labels across the top. Okay. And so we'll come back to that in a second. Why did I do it that way? Now let's finish up what they have here. For the blue ones, it says 2 smalls. So can I put that 2 anywhere? No, it needs to go in this column because previously we had agreed that this column would be small. So I can't just put that 2 anywhere I want to. Okay. And then we got 8 mediums. So, okay. Now, then it says 4 larges. Now, and then 0 extra larges. What if that had been reversed? Would we still put a 4 for that? No. You got to put the numbers where they belong. And so zeros are numbers too. And so they go where they belong. Okay. So if there's something missing, you need to put a 0 in that spot. Okay. Because look, there's no labels anymore. There are no labels anymore. I mean, yes, I have red and green, blue, but we've previously agreed that the first row means this, the second row means this, and the columns mean this. So from here on out, we don't necessarily have to label them anymore because you and I, we've come to an agreement that that's where these things go, and we don't have to have that extra stuff. Okay. So now it says make 2 new tables, one showing the merchandise sold and one showing the inventory that was left. Okay, so this is what was left. So I guess we can make another one here in the middle. Let's look at that here. So If we had 11 red small t-shirts and now we have 4, how many were sold? That'd be 7, right? 7. 7 small t-shirts must have been sold. If we got 6 left, how many were sold? I'm going to say 39 because 6 and 39 makes 45, right? What we started with. Okay, and then the same thing with 3 here. So 25, and we have 3 left, so that was 22. 22, because 22 and 3 still makes 25. Okay, and then 28, or I can even say do it like this: 28 minus 5 means there were 23 that were sold, right? And so that's how many were sold. Let me come up here, put a label on that. Sold. Number sold. Okay, and then I continue this process. So that's 21, I believe, and then 45, 17, and 32. Okay, so this is how many we started, this is how many were sold, and this is how many that were in at the end of the day. So we got these 3 different matrices. Okay, and then lastly it says, what relationships did you use to creating the 2 tables? Well, what they're trying to get at is that what did we do? We did subtraction. 11 minus 7 equals 4, and then 45 minus 39 equals 6, and so on. So the relationship was a subtraction relationship. Okay, and so all this is kind of opening the door to these different kind of operations, and we haven't really talked about what kind of rules and stuff yet, but this kind of opened it up to a little real world situation and how that might would be used and how that works. Okay, now I'm going to go to the summary first. Okay, I'm going to go to the concept summary real quickly. And so first of all, we're going to talk about dimensions, a review of dimensions. Okay, and so here's a matrix, and we usually use a capital letter to label it and name it, like matrix A, matrix B, matrix C. Previously, we pretty much always just use matrix A because we reused it over and over again. But as we go through this particular topic and expand on it, we'll end up using different letters because we'll be using more than one matrix at a time. You'll see that used in just a moment. And it says the dimensions are 2 by 3 because there are 2 rows and 3 columns. I apologize that the brackets are in the wrong place. Thankfully, in the book, they're correct, but the electronic version I have, they're misaligned often. So, and I didn't correct every one of them. Okay, but so there's our review of a matrix, how you name it, and then by the rows and columns. And so we're going to talk about what square one and things like that is. So just a quick review of that. We're going to talk about scalar multiplication, which we're increasing the scale or decreasing the scale, could be too, by multiplying by a number. Addition of matrices and subtraction of matrices. We just kind of did that, didn't we? And then dilation. Well, that's scalar multiplication as well. So let's keep running here. All right, in example 1, it says we're going to represent data with a matrix. We've already done that. So here's another scenario here. It says, what could the data values in the matrix represent? So they start off with just giving you a plain old generic matrix. And so with 2 rows and 3 columns again. Okay. And so they made up that matrices help organize information. For example, if the columns of this matrix represent sizes, small, medium, large, like we talked about before, and the rows represents shirts and sweaters. Okay. So here we go. And they've got it labeled now, right? So then the 4 can represent 4 large sweaters because it's where? It's in the sweater row and in the large column. So that's 4 large sweaters is what that number would represent. Okay. So continuing on that process. Okay. So how would we know to communicate about that 4? Is there some kind of way that we could say, hey, we want that thing over there in that little spot? that's not really good communication, is it? So we need a better way to communicate about where that 4 might be. Okay, so you can refer to an entire matrix or to an elements of a matrix. Okay, so this whole matrix is matrix A, and it has what? What are the dimensions of this matrix? It is a 3 rows by 2 columns. Okay, 3 rows by 2 columns. So that's matrix with 3 rows and 2 columns. Now, they have this generic setup to help us understand the elements. Each number that's in the matrix is called an element. Okay, and these letters and are not standardized by any means. Okay, they just picked. So they did. A lot of times we use F for functions, so they picked some letters past F. Okay, G, H, I, J, K. They just random letters. And so they're saying if we label the rows G, H, and I, and J, K for the columns, so this is not specific to a situation. This element right here would be the element in the G row and the J column. Okay, so the GJ element. And this would be the GK element. This would be HJ element. So the 4 in this matrix is the AIJ element. So it's the A standing for the 4 and the IJ being the, now, more often than not, I would say this is the 3, 2, the third row, second column element. Okay, but we'll come back around to that. But the point here is that we can talk about the entire matrix, but we also can communicate about the elements inside by using these little subscripts. Okay. Part C says equal matrices. All right. What can we know about equal matrices? Okay. What are the values of the matrices in the matrix equation? Okay. Well, it says equal matrices have same dimensions and corresponding elements are equal. So what does that mean? Okay. So the A11, that's the first column, first row, first column, that's 12. And each one, that element piece right there, they are equal. Okay. So it's 2 by 2. Each one of these is a 2 by 2, which is a square matrix. And since they're the same exact dimensions, that means the 12 equals the 12. The 0 is equal to y. Okay, so that's over here. The second row, first column, right? Second row, first column. Whoop, hold on. Whoops, sorry. That is not true. That's what felt funny for me. Second row, that would be over here. So okay, they're staying over here. That is weird. Okay, instead of making it first row, second row, they went first row in a column. Sorry about that, guys. I didn't notice that before. It just weirded me out a little bit, but that's okay. Here we go. So what they're doing is they're going to deal with the first row, first element, and the first row, second element. So they're going to deal with both the 12 and the 0 first, here, the 12 and 0. And then they're going to move over to the second row, okay, the 2x and the 10, and go from there. So let's look at this. Let me highlight something. Highlighter. So this is 1, 2, right? So there's that guy there. And so that means this thing and this thing are equal. And so what does y equal? 0. Okay. So second row, first column. So this is the second row, first column. Okay. So that guy means that this and this are equal. Well, if 2x equals 14, what does x need to be? 7. Okay. And I'm going to tell you, we're going to stop along the way and give you an opportunity to answer some little try it questions. And we'll have one very, very similar to this. Okay. And so by using equal matrices, we could figure out that y is equal to 0 and x equals 7 in this case. Easy peasy. All right. So, okay, now try it. So they've given you another matrix, okay? They're going to want you to, and they've told you what the pieces are. Column 1 lists the girls. Column 2 lists the boys. Row 1 lists the sophomores. Row 2 lists the juniors. And they want you to find each one of these elements, okay? And tell what each number represents. Okay, so let's pause that video right now and answer those questions. Okay, let's hope that you did well with that. What would that be? All right, so row 1, second column, that would be 5. Second row, first column, that would be 8. And that would be 10. Tell what each number represents. Well, okay, it said the first row, okay, this is the girls, and this is the boys, and this is the sophomores, and this is the juniors. Probably been best to label that first, make it a little easier. So the 5 is a sophomore boy, and the 8 is a junior girl. Okay, and then 10 is a junior boy. All right, so there's that guy there. Just a little quick check to see if you're following along. Okay, we're ready for example 2. Apply a scalar multiplication. Okay, Cool Threads, a clothing store, uses the matrix C to represent the prices of women's clothes. Okay, so this is called matrix C, and you see I've corrected it. The matrix is driving me crazy. The columns represents brands. Okay, vintage, casual, distressed. So vintage, casual, distressed. Okay, and the rows represents jeans and jackets. Okay, if there's a sale tax rate of 15%, how can you use a matrix operation to find the amount of sales tax on each item? Well, we're not going to use 5% ever, right? We're going to take that and turn it into what? 0.05, right? We worked on that previously. Okay. Well, I'm going to hit the next slide and all this stuff's going to go away. But remember, that is what we're referring to. Okay. All right. So we still got this guy up here. And what are we simply going to do? I'm going to do scalar multiplication because you can scale it up, okay, or scale it down in this case. Multiply each element in the matrix by a single number. It's basically just distributive property, right? It's basically just distributive property. So when you have a number on the outside of a parentheses, that means you multiply everything inside. So you see here, each element is times 0.05. 210 times 0.05. Now, I probably would reverse that, but that's no big deal. Okay, and so they have done that. And then, so if you do 320 times 0.05, you get 16. If you do 210 times 0.05, you get 10.5. 16, take 0.05, and you get 8. Easy enough. And they go through all the way through that. Okay, so if the sales tax rate is 5%, you can do this here. And what is this going to tell us? What is this telling us here? Well, go a little bit further here. Scalar product represents the sales tax amounts for each item of clothing. So when we said this was what? Oh, vintage. Vintage casual distress. Okay. So $16 for the vintage jeans, and it'll be $10.50 for tax on the casual jeans, and $8 for the distressed jeans. Okay. Hope that talking about taxes doesn't distress you. Sorry, I just slide a dad joke in there. Can't help myself. Sorry. All right, so that's scalar multiplication. Pretty easy to do. Pretty straightforward there, right? Okay, well, let's back up just a moment here. This is a good opportunity for us to review how this would work on our calculators. So I'm going to pull up my TI-84 here. Okay, and refresh our memory here. So I'm going to go, how do I get to a matrix? So I'm going to hit second matrix. That's the inverse right here. And you can kind of see where I'm hitting buttons I'm hitting down here. You can always hit pause and things like that. All right, and so we normally do A, but for the fun of it, what I'm going to do is, well, first thing I'm going to do is I'm going to hit the right buttons. It's over here. I'm used to doing it. So I'm going to do that. And then I'm going to hit the right button, but I come over to edit. What happened? It reset. I'm going to come back down to C. Now I'm only using C because that's what they're using in the book for this example. But just to show you, it isn't always A. So I'm going to edit C, and so I'm going to hit enter. What size was it? Well, it was 2 rows, enter, and 3 columns. Now, does that look about right? Sure. But what if I got it backwards? What would have happened? I would have had a 3 here and a 2 there. And you're going like, that don't look right. So thankfully, it kind of self-corrects itself, doesn't it? So I'm going to hit back up here and get these things where they belong. And say 2 rows by 3 columns. All right, and I'm just going to put in 320, enter, 210, enter, 160, enter. See it automatically went to the next row. 240, and then 110, and then 65. All right. So I went to matrix, went over to edit, and then I give it the information, and now I'm going to quit. All right. I quit. That gave me to the home screen. Gave me to the home screen. All right. So let's clear all this stuff out here. So that's all I did to put it in. You can always rewind if you need to. Now, how in the world am I going to do this scalar multiplication? So I'm going to type in 0.05, and then I'm going to come over here to second matrix. You could get used to finding that button. I'm going to come down here to C and hit enter. And so now it's going to do 0.05 times everything in matrix C. So I hit enter, and boom. Does that match what we had before? Well, it sure does. So not something you have to have a calculator for, but we're going to be needing to use our calculator for things in the future. It's just a good opportunity to get our feet under us as we get used to using these different features. Okay, so let's drop this guy out and let's go look at our next example. Example 3, we're adding and subtracting matrices. Oh, cool threads. Okay, uses matrices to keep track of monthly sales. Okay, in matrix A, that's this guy down here. Okay, and matrix B, row 1 represents the sale of jeans. So that's jeans for March, and this is the sale of jeans for April. Row 2 represents the sale of jackets. So again, it's the same thing as we did before. But the columns represent vintage, casual, and distress, just like we had done in the previous example. Brands respectively during 2 consecutive months. Very nice. Okay, here we come to example 3, add and subtract matrices. Try it. It's time for you to give it a try. For those of you who are following along in the book, you notice I've adjusted the question because we're going to deal with that in a little bit. But now it's your turn. See what happens to add these and subtract these. What would you get? What would that look like? Okay, hopefully you did that and were successful with that. What would that have been if you did the addition? And I'm going to do some shortcuts here just so you can kind of check your work. If you did the addition, that'd be -3 and 6. That makes 3. 5 plus 5 makes 10. 2 minus 8 makes -6. And 0 plus 0.2 is 0.2, or 0.2. So if you add them, that's what you get. What happens if you subtract them? What happens if you subtract them? Okay, well, that's going to be negative 3 minus 6. That gives me negative 9. And then 5 minus 5 gives me 0. 2 minus negative 8, which ends up being plus, there's 10. And then 0 minus 0.2 would be um, negative 0.2. Okay, so that's what it looked like there. And not even using a calculator at this point. That would be kind of silly. All right, so let's go on to our next example. Okay, understand matrix addition and subtraction. Well, we kind of already have a little bit of that, but they're going to go over a few pieces here. Okay, they're going to remind you here that matrices can be combined using addition and subtraction. However, they have to be the same dimensions. Okay, so here we see matrix A is 2 by 3. Matrix B is 3 by 2. Matrix C is 2 by 3. And then matrix D is 2 by 3. Okay, so if we're going to add and subtract, matrix A, C, and D could be added and subtracted. Matrix B cannot be added or subtracted to these other matrices that are provided. Now, again, we're going to find out tomorrow in our next lesson that you can multiply matrix B times any of those others, but this is addition and subtraction. They have to be like terms, and that would not be possible with any of the ones that we've been provided. Okay, let's look at B now. Okay, now look at what happened. Something interesting happened. They took matrix A and matrix D, and they added them together, and look at this happened. It's called all zeros. So let's call the zero matrix. The zero matrix. Okay. So when does that happen with regular addition? Well, 5 plus negative 5. Well, that's called additive inverse, right? When you have a negative 7 plus 7, that's an additive inverse. So when you have two matrices that are added and you get the zero matrix, that means these two, A and D, are the additive inverses. Okay? And so this is the zero matrix because it's all zeros. And it only shows up when you have additive inverses. Okay? So see, they start specifically saying that. What is the additive inverse of B? Okay? What is the additive inverse of B? So now they're starting off with, okay, something more along this lines. They're asking, I got matrix B plus what would equal 0? That's what they're asking. Well, how would I know what to put in here? Well, I would do the what? Opposite of everything in there, right? So I would have negative 6 and negative 5 and positive 2. 0 doesn't mess around. And then negative 3, it's kind of hard to see with that little tail there. And then negative 4. That's how you would do that. So this is matrix B plus the unknown. So that, that's just an X. Well, it's a capital X. When it's a capital X, this means a matrix like the unknown. Okay. And then that gives you 0, the zero matrix. And that's how you prove that things are additive inverses. Okay. It's like, is this the additive inverse of this? Well, how do you prove it? Well, you show that they give you 0 matrix. Okay. So how does A and C relate to C plus A? Well, they go through the trouble of saying A plus C gives you this matrix here, and then C plus A gives you this matrix. And lo and behold, what happens? They're saying that A plus C and C plus A are the same. So that's the commutative property, right? So the commutative property says like 2 plus 3 is the same as 3 plus 2. Okay, we already knew that. So does that mean it automatically means it's true about matrices? Not necessarily. It does for addition. We're going to find out there's one that's going to change tomorrow, but today we're all good. Okay. So hold on a second. All right. Well, they didn't bring something up just yet. Well, is that going to be true for subtraction? Was it is if it's 2 minus 3 and 3 minus 2 usually the same? Okay, then here we go. Here's example 4, try it. It says consider these three matrices, and they use P, Q, and R, nothing special. It says find what RQ is. What other matrix sums or differences can be calculated? Okay, so they said R minus Q. Okay, then it says find the additive inverses of each one of those. So it means to take each one and write a matrix that's the additive inverse of the previous one. Okay, what they gave you. So take a pause and work on that real quick. Okay, let's see how you did. See if you get the same thing as me. Here we are. I've written this up. Be careful. It says R minus Q, but they gave you Q and R. So I rewrote it in the right order to kind of help me make sure I keep it straight. And so they are 3 and 2, 3 by 2 each. So they have to be the same dimension. So that's good. So what's 6 minus 2? That's 4. 0.5 minus 2, that's negative 1.5. Okay. 3 minus 5 is negative 8. 0 minus negative 5, that's positive 5. And negative 2 minus negative 7 would be negative 2 plus 7, also known as 5. And negative 2 minus 7 would be negative 9. So that's what you get for R minus Q. Okay. Then it asks, what other matrix sums or differences could you find? Well, I could do R plus Q. I could do that. I could also do, well, that's not needed. Try that. And then I could do Q plus R. And you say, well, you don't have to write that twice. Absolutely, you have to in this case. Could we do Q minus R? Could we do, yeah, we could do that too. Yeah, we could do that. All right. So we can do all of these that have been said. Well, how about this one? How about P plus Q? No, this is 2 by 3, right? And these are 3 by 2, so that's not an option. So we can't do addition or subtraction with P at all. Okay? Not at all. Okay? Now it said do the additive inverse. Well, I'm going to do it the lazy way. So negative, 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 plus, plus, negative, plus, negative, plus, plus, negative, negative, plus, 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 negative. Now skip the zeros because plus and minus and zeros don't matter. All right, so that's the lazy way of doing it. So if you got those, then you're in good shape. And I almost forgot. So let's back up just a bit and let's take A and let's do this guy right here. Let's put A and C in our calculator. Okay. So I'm going to come back up here. Second matrix. I'm going to come over to edit because that's how you type stuff in edit. And then what size is this going to be? We're going to say A is 2 by 3. So that's 2, enter, 3, enter. And it's 5, enter, negative 7. Make sure that you hit the negative, not the minus. 3, 4, enter, 8, enter, and negative 2, enter. Okay. All right. Now I'm going to quit out of there. I'm going to go back into my matrix. And since we're trying to keep the letters straight, I'm going to come over here to edit again, come down to 3 for C, okay, because we're using A and C out of the book. And that's the correct dimensions, but the wrong numbers. And you don't really clear them out, guys. There's no real good way to clear it. You just type over it and change it as you go. All right, and C was that was 12. And then enter, and then 0, enter, 0, enter, 0 again, enter, 15, and negative 9. And then enter. Okay, so I'm going to quit. Got that edited or typed in. And so how am I going to get that to add? So I'm going to go back to second matrix and hit number 1, and there's A. Hit plus second matrix. You can do that a whole bunch, and I hit 3. There's C, and hit enter. And does that agree with what they had in the book? Well, it certainly does. Certainly does agree. But here's the cool part. Now I can do like this: second, enter, and just hit my backspace and change that to a minus. And there's the, see how that goes to subtraction very easily. Now I can then also do this. Whoops, that's not what I meant. Okay, again, not what I meant. How about second enter? It means cut paste. And then I'm going to come back over here and I want to insert a number in front. So second delete, which is insert. And now this is going to multiply everything in A and then subtract C. Can we do that? Sure enough, and it did not give me an error message. So just to, you don't really need the matrix function on the calculator to do anything in this assignment, but I thought it might be good to take an opportunity to review how that would be done, because you will need that eventually in our next sections. Okay, so very quickly here, I want to just kind of touch on this. Using matrices to translate or dilate figures, okay? I kind of just want to look over the setup more than anything else. So they're starting off here. In this diagram, AB is translated 4 units to the right and 2 units up. So I'm going to take the AB and go 4 units to the right and 2 units up. So if I take this spot here and go 4 to the right and 2 up, I land at P, don't I? If I take this over 4 to the right and 2 up, I land at Q. Okay. It's also dilated by a factor of 1/2, which means what it was, 1/2, so shrunk it up by half, didn't it? And so what's half of 2? 1. And what's half of 6? 3. What's half of 8? 4. What's half of 4? 2. Okay. Well, those kinds of things make sense. And see how this ordered pair turns to those, looking at the graph. But what does that look like if you take that same information and put it into a matrix? Okay, so we're going to say the original is AB. That's called the preimage, basically what you start with. Okay, now where did this 4242 come from? Well, if you didn't notice, we said the rows are going to be what? X, and this is going to be Y, correct? So let me actually put that information in here. We said this is going to be X, this is going to be Y, and this is what? Point A and point B, right? Well, this is just how much they're going to do. So we're going to go 4 to the right, that's an X on both of these, and we're going to go 2 up on both of the Y's. So these are all X's and Y's. So that's an XY, 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 XY. Except these are how far you're traveling. Okay, and so that's where it landed. And did it not? 6, 8? Because 2 plus 4 is 6. 8 plus 4 is 12. So we did this by looking at the ordered pairs and looking at the graph. But if you set up a matrix, okay, this shows you it's going to the right 4 up 2. Okay, because we said this is X and that's Y. So that's how you can kind of use what we already know and use it and track it using a matrix. Okay, so just a quick review. We name things by capital letters, A, B, and C. If it's an unknown matrix, we use the capital letter X, just like we do the lower X for a variable. And this has 2 rows by 3 columns. And A sub 1, 3, the first row, third column is a V. And so that's how you would tell me about an element. Scalar multiplication, basically a distributive property. Adding and subtracting is just fine. And you got to have the same exact size because you have like terms. And here we are back. That's talking about stuff in section 1 of topic 10 in our SAVVAS book. And how can I interpret matrices and operate with matrices? So as always, this is Mr. T. Hoping that was helpful for you. Bye-bye.